same in series, and V is voltage, is the same in parallel. Current is conserved if you remember from the last section, we didn't get charge out of nowhere. The charge was also conserved. Current is charge per second, so current needs to be conserved. So current doesn't get used up, charge doesn't get used up. So in our picture here, the blue arrow, some goes down as a red arrow, some goes as the green arrow, but the total, which is both coming out of the battery and going in the battery, would be the sum of those. So in series, each of the components will use up some of that pressure, some of that voltage. In parallel, they would get all of it. So here's a picture, and this shows us what our potential is. So if I go from D to E, I gained 12 volts of potential. I go through my wire from E to A. So this is 0 ohm resistance for a wire as far as we're concerned. Then when I go from A to B, I need to lose some of this voltage. So I lose 7 volts, and that leaves 5 volts for this one. And then I lose the last 5 volts, and then I end up through the wire again. So no loss at all here, back to the other side of our battery. Keep in mind, the battery has no idea what resistor is first. So if I move the 400 ohm resistor after the 290, it's still going to lose 7 volts on the 400 ohm resistor. That battery feels all of those components at once. It doesn't feel one and then feel the other, right? All of these things already have electrons in them before you hook up that battery. And you're just causing them to move. So this is called, it's one of Kirchhoff's loop rules. And the idea is that the sum of the changes in the potential around a closed loop is 0. So all the potential gets used up. All right, so to solve these problems, we're going to make a V equals IR chart. Then we're going to find our total resistance, our total current, and our voltage, and we're going to